G'day. In probability theory, a lot of people just say the word and means multiply. They just say and means multiply. Well, I don't know what that actually means, so today I want to explore that claim. In what sense is that true? I mean, first of all, I figure out what it means, and then what sense is it true? Because I'm sure there are subtleties and nuances to a statement like that. So what's going on? Well, first of all, people must be talking about double-barreled experiments where there's an and connecting two different actions. For example, here's the example we did before. Suppose I roll a die and then flip a coin. So that's a double-barreled experiment. Do one thing, roll a die, and then flip a coin. Now, my question we asked before, what's the chance of me seeing a 6 and then seeing a head? So sometimes I want to see a 6 and head. So there's the word and really in there. I didn't write the word and, but that's what they mean by and. Doing one action, doing a second action, I want to see result from the first action, and I want to see a particular result from the second action. So that's what they mean by and. So the question is, should I just multiply probabilities in some sense? What's really going on? So let me analyze this again. Let me draw the garden path system. We actually answered before. We got the answer 1/12, I believe. But let me do a weighted garden path system this time to show what's going on, because I have a feeling that might reveal what the word and multiply mean together. All right, here goes. So there's going to be a want house, and there's going to be a don't want house. All right, that's fine. And we'll send people down a garden path and they'll split a coin to the first action, rolling a die, and then split a coin to the second action, flipping a coin. So here they come. So they come down the path, grand, and the first thing these people are going to do is roll a die. They'll either get a 6 or they'll not get a 6. All right. Those that don't get a 6, straight to the don't want house. Fine. Those that do get a 6, we'll consider them. We'll have them in our considerations. I mean, these people can flip coins, do whatever they want. Doesn't matter. They're going to the don't want house, whatever they do. Flip a 6, roll a 6, then they come along and flip a coin. In which case they either get a heads or they get a tails. They get a tails to the don't want house, to the heads. That's what I want. All right, so there's the garden path system, but I'm going to be careful. It's actually weighted, because we know when you roll a die, there's only 1/6 chance of getting a 6, 5/6 chance of not getting. So actually 1/6 of the people go this direction, 5/6 of the people go this direction. So it's actually imbalanced there. And those that go on to flip a coin, yes, half of them go to get a heads and half will get a tails. So there are the weights on that diagram. And now we can see what the area model says. Because actually I can see that 1/6 of the people are going along what we want, and then 1/2 the people going along what we want. And that means my area model is 1/6 are going along what I want, so 5/6 aren't. And then half the people are going along what I want, 1/2 aren't. I'm seeing right there 1/2 of 1/6. So I just multiplied the probabilities on that path right there. Oh, I want a 6 and a head. I multiplied that probability and I multiplied that probability because it actually is 1/2 of a 6 of the picture. Multiplying those numbers is actually correct. So maybe that's what people mean by and. Multiply the probability on that part of the path times probability on that part of the path. Now, I'm a little bit nervous about that because I think that 1/2 is deceptive. These are all the people that have flipped ahead given that they've just rolled a 6. But the thing is, coins are just like their own independent objects. They don't care what you did beforehand before you flipped it. You know, if you rolled a 6 beforehand, you flip it, 50% chance you'll get a heads. If you stood on your head before you flipped it, doesn't matter. Still 50% chance of getting a head. If you're wearing purple trousers and you flip the coin, it doesn't care. Still 50% chance of getting a head. This is a very independent object. This answer here will always be a 1/2 no matter what went on beforehand. But there's the subtlety. Because in some experiments, you go down garden paths, the probabilities can change. Because we've seen an example like that already with a bag with some colored balls in it. So let me show you that actually, yes, we are getting a fraction of a square. We are multiplying probabilities, but we want to be careful about what these probabilities along the garden paths actually are. So let me clean the board and pull up the other example we did where things change along the way. Because that, I think, is the subtlety behind that statement. All right, so let me clean the board. I'll be right back. Okay, so here's the other example we did, another double-barreled experiment. It's about a bag that contains 2 red balls and 3 yellow balls. I pull out a ball at random, note its color, and put it aside. Okay, then there's 4 balls left. I pull out another ball at random, note its color, and then put that aside as well. So I pulled out 1 ball, put it away, pulled out a second ball, put it away, and the question was, what are the chances that we'll see a red and then a red? That I pull out a red ball, and then we pull out a red ball. All right, so there's a double-barreled experiment, and it's got the word and. In fact, I wrote the word and this time. So let me show you the garden path we did for this as well. We did it earlier on, but it's going to be a want house. Great. It's going to be a don't want. Whoops, don't want. All right, whoops, already marked in a box. Oh, I'm making smudges. Uh-oh. Okay, you're with me, I think. All right, so first thing we do, people come along and they'll encounter one of these bags which contains 2 red balls and 3 yellow balls, and they can either pull out a red ball or they can pull out a yellow ball. But we know it's weighted. But we looked at the weighting before because actually there were 2 red balls in there. They've got 2/5 of the people will pull out a red ball right there, and the remaining 3/5 of the people will pull out a yellow ball in an ideal situation. So there's actually a weighted diagram right there. Those that pull out a yellow ball, they might as well go straight to the don't want house. They can do whatever they want, pull out more balls, do whatever they want to do, doesn't matter. They're going to the don't want house. Those that pulled out a red ball first off the bat will keep going in my considerations because they're going to go to the bag again and pull out another ball. So they'll come back and reach a fork where they go back to the bag. Now, think of the bag they're encountering. It has 4 balls in it, and they've already taken out a red ball, so what's in that bag is 1 red and 3 yellows. Now they can still either pull out a red or pull out a yellow, but now the probability has changed because they've got rid of 1 red, there's only 1 red left. That is, they have a 1 in 4 chance of pulling out that red, 3 in 4 chance of not. That is, 1/4 of the time, 1/4 of these people will go to the want house, and 3/4 of these people will go to the don't want house. Yes? All right, so now I'm seeing some probabilities along the path to the want house, which means my area model says, okay, first of all, 2/5 of the people moving along how I want, 3/5 go straight to the don't want house. Of those 2/5, 1/4 of them go along to what I want, 3/4 don't, so there is the region of people that end up in the want house. And that really is 1/4 of 2/5 of the square. That really is multiplying 1/4 and 2/5. 1/4 of 2/5 of the square. So yes, this word and has led to multiplication in the actual arithmetic. But what are we actually multiplying? We're multiplying those numbers along the garden path. Yes, this 2/5 is the probability of pulling out a red ball right off the bat. Great. But this 1/4 is not the same probability pulling out a red ball because this has changed things. This is the probability of pulling out a red ball given that we previously pulled out a red ball. Got that? Because with the coin, we had the probability of flipping a heads given that we previously rolled a 6. The trouble is the coin didn't care about what we did previously. This experiment does care about what happened previously. Therefore, the probabilities have adjusted themselves. We went from 2/5 to 1/4. So that's the subtlety. That's the subtlety. And in some sense does correspond to multiplying, but you're multiplying probabilities that may have changed along the way. So that's the probability of pulling out a red ball right off the bat. This is the probability of pulling out a red ball given that you previously pulled out a red ball. This probability here is the probability of pulling out a yellow ball given that you previously pulled out a red ball. So you can actually, all these numbers here have adjusted probabilities. So that is the multiplication problem in the multiplication principle in probability theory. All right, so it's about multiplying my maybe absolute probabilities and adjusted probabilities for given what's happened before. So what I want to do now is be very formal and write the proper multiplication principle on this board once and for all, because I don't think many people spell it out for exactly what it is. I want to be really clear on this does and mean multiply idea. So let me clean the board. I'll write up the principle. I'll try to be neat with my handwriting. I'll do it beforehand so you don't hear me squeak, and then we'll talk about it. So back in a moment. Okay, so here's the general multiplication principle in probability theory. Suppose one performs one task in the hopes of getting outcome A, task number 1, and then performs a second task in the hopes of getting outcome B, 2 tasks, so a double-barreled experiment. To work out the probability of seeing A and then B, do the following. Work out P of A, the probability of seeing A in the first task alone. Just do the first task and we'll get the chance of seeing outcome A. And then do P, what I wrote as B/A, which is the probability of seeing B, CB, under the assumption you've just seen A in the first task. So this is called conditional probability. What are the chances of seeing outcome B given that you've just seen A in the previous task? That could be a different number, as we saw with the bags. It changed from a 2/5 probability to a 1/4 probability, pulling out a red ball from a bag. All right, so this is the adjusted probability. Then the multiplication principle says then the probability of seeing A followed by B equals, now people just say usually seeing A and B, but I'm being very clear, you're really asking about seeing outcome A followed by outcome B is actually the product of these two probabilities. It's this conditional probability times this absolute probability. That is the multiplication principle. And it really is the area model, the fraction of a square. If I did the area model here, I'll do it in pink, a little space. You will first do the first experiment and you hope to see some fraction of the square that corresponds to outcome A. That fraction is what we call the probability of A. And then within that part of the square, we hope to see outcome B. That is, some portion of this will be, this part is what we want to see. That is, a fraction of the square that corresponds to seeing outcome B under the assumption we just saw A. So that is really this fraction, P of B slash A, of that fraction of the square. The multiplication principle. All right, or if you like, going down the garden paths, it really is the first probability on that path and then the adjusted probability on the path to get to the want house. Either way you want to look at it, fraction of squares, be very clear what the actual fraction of the fraction is. It's a conditional probability. Getting B under the assumption you've just seen A in the first task. Either way you look at that, here it is, the multiplication principle. It is subtle, and the reason why people don't usually understand it very well is they give examples about coins that don't care about what happened beforehand. So that is where it gets murky. So it's good to do examples where the second experiment does care about what happened beforehand, because that's what's really going on.